At this stage, it is good to do some housekeeping and cleaning of our formalism. We introduced amplitudes, m, describing interactions in scattering and decays of particles, and went on to calculate them with Feynman diagrams. We gave hand-wavy arguments about not including propagators of the external lines. We also choose to not write explicitly the overall energy momentum conservation, but I'll assume that it is always here, as nobody in principle is crazy enough to calculate something which does not conserve an overall energy momentum. We also used these amplitudes to compute cross-sections and decay rates. So in the next few videos, we are going to attempt to remove some of the hand waviness of these arguments and try to put them on more solid grounds. And to do that, we first introduce the S-matrix. So we consider the scattering between particles, which are incoming with plane waves P1 and P2, and then after the collision, end up in other plane waves, P3, P4, etc., up to Pn. These are called asymptotic states. So the initial state is the state of the system when the time goes to minus infinity. And F is the state of the system when t goes to plus infinity. So if we set a reference of time t equals 0 when the collision occurs, we see that we need to propagate I, the initial state, forward in time from minus infinity to t equals 0, and F, the final state, backward in time from t equal plus infinity down to t equals 0. And for that, we will be using evolution operators both forward and backward in time. So the overlap between these two states gives us the amplitude of probability for the collision to occur, and that defines the S-matrix element connecting these initial and final states. It is usual to write S equal 1 plus IT, where T is not the time now, but another matrix. Sorry for the confusion in the notation, but it is quite standard. And we have the identity here to account for when nothing happens, while T is the interesting part, accounting for the change of state. Factorizing out the energy momentum conservation, we can then define our scattering amplitude M. So M is an invariant matrix element describing the non-trivial part of the S matrix and accounting for how particles interact. So this scattering matrix element M accounts for the dynamics of the collision. And if we want to get cross sections, we need to include, as we saw, kinematics term for the incoming and outgoing channels.